Everyone knows the great names: Stephenson, Gresley, Chapelon. When historians trace the lineage of modern railway engineering, the names they reach for are British, French, American. The workshops they cite are in Doncaster, Crewe, Philadelphia. The prototypes that supposedly changed everything were born in those places, tested on those tracks, and celebrated for generations. Almost nobody mentions Newport. Not Newport in Wales, not Newport in Rhode Island, Newport in Victoria, Australia. A suburb of Melbourne, sitting on the edge of Port Phillip Bay, home to a locomotive works that by 1938 employed more than 4,000 men and occupied more than 30 hectares of manufacturing floor. A facility that, in that year, quietly produced a prototype passenger vehicle using construction techniques so far ahead of their time that when British railway engineers finally examined the drawings, more than a decade later, they asked, with genuine embarrassment, why nobody had told them sooner. This is the story of that prototype, of the men who built it, of why it worked so extraordinarily well, and of why, despite reshaping how passenger rolling stock is designed and manufactured across 3 continents, it never quite received the recognition it deserved. Newport Workshops was established in 1889, built from scratch on swampy ground that required years of drainage and fill before construction could even begin. Victorian Railways needed a centralized facility to maintain and eventually build its own rolling stock, and Newport became that facility, gradually, yet stubbornly, against the kind of budget constraints that seemed endemic to colonial-era public works. By the early 20th century, it was producing locomotives, passenger cars, and freight wagons of genuine quality. But quality alone was never the point. The engineering culture that developed inside those brick buildings, inside those machine shops smelling of oil and hot steel, was one of problem-solving under constraint. Victoria's railways ran on broad gauge, 5 feet 3 inches, which meant imported British designs rarely fitted without modification. That necessity of adaptation over decades produced engineers who thought differently, who questioned inherited assumptions, who asked not just whether something worked, but whether it could be made to work better with fewer materials, less weight, greater reliability. By the mid-1930s, that culture was about to encounter the greatest constraint it had ever faced. The Great Depression had struck Victorian Railways the way it struck every public institution, with savage ferocity. Rolling stock maintenance budgets were slashed. New construction was deferred year after year. The passenger cars in service on Victoria's main lines were by 1935 among the oldest in the country. Many had been built before the First World War, riveted together from heavy steel sections in the tradition of the 19th century, robust and enduring, but increasingly unsuited to the demands of modern operation. They were heavy, enormously heavy. A standard VR passenger car of that era tipped the scales at around 38 tons, which meant the locomotives hauling them burned more coal per mile than equivalent services in Europe or America, wore out their running gear faster, and strained track infrastructure that itself had been starved of investment. The solution was obvious in theory. Build lighter cars, but lighter meant thinner steel, which meant weaker structure, which was not something Victorian Railways was willing to accept. The workshop engineers had watched what happened when foreign manufacturers prioritized weight reduction over structural integrity. They'd seen the results in accident reports. They were not interested in repeating those mistakes. What they needed was a way to build lighter without building weaker. And in 1936, a chief draftsman named Harold Freeling, a quietly methodical man who had spent 17 years studying every welding technique and structural analysis paper he could obtain, proposed a solution, not revolutionary in concept, revolutionary in application. Freeling's insight was this: the conventional passenger car body drew most of its structural strength from its underframe, a massive, heavy steel chassis that everything else sat on top of. That underframe was overbuilt. It had to be, because the body panels, the roof sections, and the side walls contributed almost nothing to overall structural rigidity. They were essentially dead weight wrapped around a load-bearing skeleton. But Freeling had been studying aircraft construction. He'd been reading about stressed skin monocoque structures, and he believed, with meticulous mathematical backing, that if a passenger car body were welded, not riveted, welded, into a unified stressed skin structure, the entire shell would carry load simultaneously. The underframe could be dramatically reduced. The weight saved would be profound. He put the numbers to his supervisors. The weight of a standard VR car could potentially be reduced from 38 tons to just under 27, a saving of more than 11 tons per vehicle. On a 12-car express, that was more than 130 tons of train weight simply eliminated. It took 2 years to get approval for a single prototype, 2 years of committee meetings, of engineering reviews, of consultations with the railway's metallurgists about weld quality and fatigue life. This was not timidity, but this was Victorian Railways doing what it always did, being absolutely certain before committing. When approval finally came in 1938, Newport workshops received authorization to build one experimental passenger car to the stressed skin welded design. One car, no fanfare, no announcement in the press. The construction process alone was a departure from anything previously attempted in Australian manufacturing. Conventional riveted construction relied on a large workforce of relatively general-purpose tradesmen, driving hot rivets into pre-punched holes, an imprecise process with known tolerances. Welding demanded something different: precise joint preparation, consistent heat control, systematic inspection of every weld seam. Newport's welders were retrained. Fixtures and jigs were built to hold the car body sections in exact alignment during assembly. A quality control protocol was developed, borrowed partly from aircraft manufacturing and partly from Freeling's own research into European practice, that required every structural weld to be tested to a defined standard before the next section could be attached. The car that emerged was, by every external measure, unremarkable. It looked like a railway passenger car. It had seats and windows and doors. What made it extraordinary lived in its structure, in the precise geometry of its welded joints, in the engineered distribution of stress through every panel, in an underframe so light it seemed almost impossibly slender to anyone accustomed to the old construction methods. Testing began on the main Geelong line in late 1938. The results came back from the testing engineers in language unusual for official documentation. Words like exceptional, words like beyond expectation. The car rode more smoothly than any comparable vehicle in the VR fleet, partly because of its lower center of gravity and partly because Freeling's team had simultaneously developed a revised bogie design, also welded, also stress-analyzed, that tracked the rail with greater precision at speed. The ride quality, measured by instruments and confirmed by the frank testimony of every staff member who rode in the car, was substantially superior to anything that had come before. The weight figures were verified: 26 tons, 800 kilograms, more than 11 tons, lighter than the riveted equivalent. The calculated fuel savings on a full express service, extrapolated across a year of operation, were significant enough to attract serious attention from the VR Commissioner himself. By 1939, Victorian Railways had committed to constructing a fleet of cars to the new design. That fleet would eventually become the spirit of progress, not just Australia's most celebrated express train, but a mobile demonstration of what could be achieved when workshop engineers were given the freedom to question fundamental assumptions and the rigor to back their questions with calculation. What happened next is where the story becomes complicated. The Second World War interrupted everything. Newport workshops pivoted to war production, manufacturing components for aircraft, armored vehicles, and naval equipment. The new passenger car program was suspended. When it resumed, the world had changed. Railway engineering priorities had shifted, and the opportunity to formally publish, to patent, to demonstrate the Melbourne design to an international audience, that moment had quietly passed. British engineers visiting Australia in the late 1940s encountered the Spirit of Progress cars on the Albury Run and were reportedly startled by their quality. Correspondence preserved in the Public Record Office. Victoria documents at least one formal inquiry from the British Transport Commission in 1951, requesting detailed drawings of the VR welded car body construction method. Those drawings were supplied. Within 3 years, elements of the stressed skin welded construction philosophy had appeared in new British Railways Mark I carriage design documents without attribution. Not through any deliberate appropriation. The techniques had by then been independently developed in multiple places, but because the knowledge had circulated through the quiet channels of professional correspondence, shared drawings, and the visits of engineers who went home and built what they'd seen. The irony is precise and particular. Victoria, in its isolation, had arrived at a structural engineering solution ahead of the mainstream. Had Newport been located in England, had Freeling been employed by a railway with better connections to the international engineering press, the Melbourne prototype would likely appear in standard textbooks today. Instead, it exists in the engineering history of the railway it was built for, acknowledged by specialists, unknown to almost everyone else. Harold Freeling retired from Victorian Railways in 1952, received a modest commendation in the Departmental Gazette, and died in 1971. His obituary in the Argus mentioned his long service. It did not mention the prototype. It did not mention the weight savings, the weld protocols, or the drawings that crossed oceans. The questions that story raises are not comfortable ones. How many other engineering breakthroughs sit in archives exactly like this? How many solutions to problems that cost the world's railways billions in wasted weight, wasted fuel, worn track? How many of those solutions were found quietly in workshops far from the centers of engineering prestige, and then simply lost in the correspondence files of institutions that lacked the publicity machinery to tell the world what they'd done. Newport workshops closed in 2013, yet the buildings still stand. Some have been converted to other uses. The rail lines that once carried test runs for the prototype run into the workshops from the south, overgrown now at the edges, the steel gone faintly orange where the trains no longer pass. But every modern passenger car, in Europe, in Asia, in the Americas, carries within its welded, stressed skin structure a philosophy of construction that someone in Melbourne understood first. The numbers are in the archives, the drawings are verifiable, the weight savings multiplied across 80 years of global fleet construction, across millions of car kilometers, across uncountable tons of coal and diesel saved, add up to a legacy larger than any obituary captured. History remembers what gets published, what gets named, what gets claimed. Newport built something that mattered, and the world used it without ever quite knowing where it came from.